that if instructions have to be executed, then they must be in the physical memory. So any program which is lying on the disk, it has to be taken to the RAM or the physical memory so that it can be executed by the processor. Now, if the size of the main memory is limited, that means the size of the program will also be limited to the size of the physical memory, because now you can take only that size of the program which can be fitted into the RAM. So in that case, the size of the program will now be limited. But we have seen that in many cases, the entire program is not needed. There are certain codes which handle error conditions. Then there are static memory allocations to arrays, and then certain features of the programs which are not run, so they need not be taken to the RAM when the program is loaded into the main memory. Also, the entire program may not be needed in the memory at the same time. That means it is not necessary that the whole program is to be taken to the RAM for execution, because the complete program is not needed at the same time. So the ability to execute a program only partially in the memory can have many benefits. That means when we take a program to the main memory, we will take only a part of it to the RAM. So what will be the advantages of doing that? So now the program size is no longer constrained by the amount of the physical memory which is available. Now since the whole program is not being loaded into the memory, that means we can have a larger program which will be kept in the hard disk, and we can take only a part of that program to the main memory, because the main memory is smaller in size as compared to the secondary storage. Now if each program, if it takes less physical memory, because we are taking only a part of that program to the RAM, that means more programs can run at the same time. We can take parts of multiple programs and put them in the RAM. And these programs, they can run concurrently. That means sometimes one program can run and at another time another process can run. This increases the CPU utilization and throughput. Also, since we are taking only a part of the program into the main memory, that means less input output will be needed to load that program, or when swapping is done to the swap space. So when we know that a program which is currently on hold, that means it is either doing an input output, so it is blocked or suspended, so it can be taken to the swap portion of the disk space, and then less IO is needed because we have taken only a part of the program to the memory. So to execute this part, when we can take only a part of the program to the main memory, this concept can be implemented using virtual memory. So the virtual memory, it involves the separation of the logical memory from the physical memory. So the logical memory is the memory which is what is perceived by the developers, and the physical memory is the one which is actually available in the system, physical memory or the RAM or the main memory. So this virtual memory concept, it allows a large virtual memory to be provided for the programmers, even if a smaller physical memory is available. So now the developers or the programmers, they are not limited by the size of the physical memory that will be available in the system. The programmers use the concept of a large virtual memory. So here is a representation of the virtual memory where this whole program is divided into pages. So there is a sequential set of addresses, and these set of addresses, they are divided into pages. So this is page 0, then page 1 and page 2 and so on. So this you can see is what is seen by the developers as a consecutive or sequential set of addresses. Then there is a memory map. That means this memory map will say which page belongs to or is kept in which part of the physical memory. So this is the virtual memory which is seen by the developers as a consecutive set of addresses. Now this physical memory or the RAM or the main memory, now in this we will take only that page which is actually needed. So the page of that virtual memory program will be put according to the memory map into a particular part of the physical memory, and this memory map will also keep track of where these pages are available on the backing store. From the backing store, the pages can be taken into the RAM and can be taken out of the RAM also. So this virtual memory, which is in the form of pages, is put in the backing store. And from here, from the backing store, the pages will be taken to the physical memory. So this virtual memory is only a concept of consecutive addresses which is seen by the developers. So just to repeat once again, this virtual memory is the separation of the logical memory or the virtual memory from the physical memory or the actual physical memory which is available in the system. Now only part of the program that can be taken into the memory for execution. So whichever part of the program requires, whichever instructions are being required by the processor, only that part of the program can be put into the memory for execution. Also, now since this virtual memory is using the logical address space, that means it can be much larger than the physical address space. Now this program will be kept on the hard disk or the secondary storage, which is much larger in size. That means now the program is not limited by the size of the physical memory. So the physical address space, which is in the main memory or the physical memory, now this address space can be shared by several processes. So if this is the RAM, then if this space is being used by P1, a part of process P1, and when it is taken to the swap space out, same space can be used by another part of another program. So now more programs, since they can be put or loaded into the memory, so you can have multiple parts of multiple programs loaded into the main memory, and these programs can run concurrently. Concurrently means they are available in the main memory and they can be run by the CPU as per some scheduling algorithm. So the logical view of the processes which are stored in memory is consecutive addresses which are consisting of pages. This is the logical view, and the physical memory is organized in page frames. So if we look at this, the logical view is that the address space is a consecutive address set and the physical memory is organized as frames, and each page can be put in a particular frame. You can check my earlier lecture in another playlist, which is CO50 of the Organization and Architecture playlist, to see more concepts on virtual memory. We have also seen that the address translation from the logical memory or the logical address to the physical address is taken care of by the memory management unit, which we have already done in one of the videos earlier. So this memory management unit maps the logical address to the physical address. Let's come to the concept of demand paging. We know that we can bring the entire process into the memory at a time, but we need not require the entire program in the memory. We do not need the entire program in the memory initially. So what we can do is that we can bring a page, that logical address space, memory only when it is needed. That means only is demanded. So what are the benefits of this? That if we are bringing only a particular page, that means less input is needed. So there is no unnecessary output. That means those pages which are not required are not being brought into the memory. So we are utilizing the time that is needed for output for some other purpose. We are not wasting time on input output. Also, since only a particular page is brought into the memory, less memory is needed for that particular process. There is a faster response as more users can be entertained by bringing their processes into the main memory. So whenever a page is needed by the microprocessor, there is a reference to it. So the processor or the CPU sends out an address. That means it requires an address which is in a particular page. Now this reference to that particular address will first be checked whether it is a valid reference or not. That means if the program or the process is referring to a particular address in space or trying to access some other process. So this reference needs to be checked. If it is a reference, the process is aborted or terminated. But if the page that is required is not currently brought into the memory from the swap space or the secondary storage. So the basic concept of demand paging is that load a page in the memory only when it is needed. So when a process is executing, there is a possibility that some pages will be in the memory and some pages will be there in the secondary storage. So how does the system distinguish whether the page is in the memory or it is in the secondary storage? So we need some hardware support to distinguish between them. So for this we have what is known as an valid invalid bit, which is also put in the page table. Concepts related to page table, please check my earlier videos. So with each page table entry, there is a valid invalid bit. We know that in a page table, for each, this is the virtual page. This over here, for each virtual page, there is an associated entry in the page table which will specify that the page is available in which frame number. So frames are the like the partitions which are available in the main memory, and the page size is equal to the frame size. So any page which is brought into the memory is kept in a particular frame. So this shows that virtual page 2 is available in frame 3 of the main memory and it is valid. So V is referring to that it is in memory. So you can keep, if it is in a binary form, you can assign 1 for valid and I, which is or invalid, can be represented by a 0 bit. So valid shows that that page is available in the memory and invalid shows that that page is not in the memory. Initially, the valid invalid bit when the system starts is set to the invalid state for all entries, which shows that no previous data which is available in the page table is valid. And during MMU address translation, that means the processor has sent out an address and the MMU is doing an address translation from the logical to the physical address. If the valid invalid bit is I or invalid, that means the page is not in the memory. So this results in a page fault. Page fault means that the processor is referring to a page which is not in the memory. So it is a page fault and now it has to be brought from the secondary storage to the main memory. So let's say this is the logical memory representation. There are 8 pages, 0 to 7, and this is the page table. For each entry of the page, like it shows that page 0 of the logical memory is available in frame number 4 and it is currently valid. Similarly, page 2 is available in frame 6. So you can see that page 0 is available in frame 4. So if this is the physical memory, you can see that this is frame 4 and this is page 0. So the contents of page 0 are available here. Similarly, page 2 is available in frame 6. So you can see that the contents of page 2 are available in frame 6 of the physical memory. So all these pages of the logical address space, they are available in the backing store. So this is page 0, this is page 1, page 2 and so on. So they are brought into the physical memory from the backing store as and when they are needed. That means demand paging happens. If there is a page fault, then how is it handled? So first of all, if there is a reference to a page by the microprocessor, first the MMU will check whether the reference is valid or an invalid memory access. So if the memory reference is invalid, the operating system will terminate the process. If the reference was valid, that means it is referring to its own address space and not to any other address of any other process, then if it is a valid reference and if the page is not in the memory, we are having a page fault. Now the operating system will be sent a trap signal. So what the operating system has to do now is to find a free frame in the main memory. It has to swap the page which is required into that free frame via a scheduled disk operation. That means the OS will send a request to the disk that it requires this page, and now when that page is obtained from the disk, it will be brought into the frame. Or also it will reset the page table to indicate that the page is now in the main memory. That means it will set the valid bit to a valid bit representation, which could be either 1 or 0 depending upon the system. And whichever instruction had referenced that page, it will be restarted. So if we look at the sequence of events, there was a reference to a particular address, and when that address was checked in the page table, it was found that the entry for that was invalid. This invalid entry, that means there is a page fault, so a trap signal has been sent to the operating system. The operating system now will send in a request to the hard disk requesting for the page, and when that is scheduled, when that request is scheduled, that page will be brought into a free frame which has been identified by the operating system. Also, now the page table will be reset and this invalid bit will be changed to a valid representation, and then finally the instruction which had referenced to it will be restarted. So when we talk about the free frames, where are these free frames available? So whenever there is a page fault, we know that the operating system must bring the desired page from the secondary storage into the main memory. So the operating system maintains a free frame list. So this is a pool of free frames for satisfying such requests. Typically, the free frames are allocated using the zero fill on demand technique. That means whenever a frame is allocated to another page, or the content of the frame is erased before it is allocated. Now when the system starts up, all the available memory pages or the frames, they are placed on the free frame list. So the number of frames which are available in the memory, they are all put on the free frame list. And as the processes start running and as the free frames are requested, the size of free frame list gradually shrinks. Let's take a look at the performance of demand paging. If there were no page faults, that means the effective access time would be equal to the access time of the memory. So whatever is the time required to access the main memory and refer to that particular page, that will be the effective access time. But if there is a page fault, that means now that page has to be read from the secondary storage and then brought to the main memory, and then only the desired address can be accessed. Let's suppose the main memory access time was MA, and let's say the probability of a page fault is P, and this probability can be between 0 and 1. If probability is 0, that means there are no page faults, and if probability is 1, that means every reference is causing a page fault. So now the effective access time becomes 1 minus P times, because 1 minus P is the time when the page fault is not happening, into MA. So the times when the page fault is not happening, the time required will be MA, which is the main memory access time, and plus that many times the page fault happens, we will have to service it, and so whatever is the time required to service that page fault, that will be required. So the effective access time now becomes 1 minus P into MA plus P into whatever is the page fault service time. If MA is 200 nanoseconds and if the time required to service a page fault is 8 milliseconds, then the effective access time will be, using this formula, 1 minus P into 200 plus P into this, because now we have to convert the millisecond into nanosecond to be consistent. So this becomes 200 plus this. Now if P is 1 out of 1000 accesses, that means P is 0.001, that this is the probability of a page fault, then the effective access times becomes 8.2 microsecond. Otherwise it was 200 nanosecond. Now the effective access time has become 8.2 microsecond. That means the system slows down by a factor of 40. So even if there is a very small probability of a page fault, still the system slows down by 40. So the requirement is that the number of page faults should be minimized.